What's up, everybody? So today I'm going to be going over our first physics lesson. So this is just about kind of like numbers and how to interpret them, and like magnitudes of numbers. For the first one, we're going to be going over like the OpenStax book. So if you go to OpenStax, I think .org it is. I'll link it in the description. You'll have that's just the book that I'm going off of. So these are just a bunch of practice problems. This says number 14. Says find the order of magnitude for basically the thing we're studying. So let's see. Okay, so the first one, and then we're going to use these in later calculations. I'll link like a little spreadsheet. So it says the mass of the Earth's atmosphere, and it gives you the number. Um, 5.1 times 10 to the 18. 5.1? Yeah. Times 10 to the 18 kilograms. So this one, you're going to round up, and you're not going to be paying attention to this. You're going to be paying attention to what the root of 10 is. The root of 10 is approximately, I think, like 3.1. So since this is greater than 3.1, the order of magnitude is going to be 10 to the 19. So that's going to be the estimated order of magnitude for the mass of the Earth's atmosphere. The next one is going to be the mass of the Moon's atmosphere. And that is going to be 25,000 kilograms. Which, just in scientific notation, is 2.5 times 10 to the 4th kilograms. So this 2.5 is less than 3.1, so you don't have to round that. That's just going to be a magnitude of 10 to the 4th. So this one's A, B. So mass of Earth's hydrosphere is C. That is going to be 1.4 times 10 to the 21st. Now 1.4 is less than root 10, 3.1. We're rounding like that because the number that affects it most is the powers of 10. In this case, because we're estimating magnitude, you'll see later in this video there's a big difference between like 10 to the 9 and 10 to like the 11. I'll show you an example of that shortly and how vastly different those numbers are. So 1.4 times 10 to the 21st, that means the order of magnitude here is going to be 10 to the 21st power. And let's see, mass of the Earth is next, so let me erase this. So mass of the Earth is going to be 5.79 times 10 to the 24. Now this is greater than 3.1, so we're going to estimate the order of magnitude to be 10 to the 25th. Next is mass of the Moon. That one is D. So E mass of the moon. And 7.34 times 10 to the 22nd. This is going to be greater than 3.1, so we're going to estimate 10 to the 23rd. It's going to be the mass of the moon. And if you notice, that's just a difference of 2 powers of 10, and the Earth is quite a bit bigger than the moon. So that's already kind of an idea. The goal of this video is to kind of like put numbers into perspective. You'll see when we start working the problems that are going to use these estimations for order of magnitude, and it's pretty wild. So 10 to the 23rd, yeah, okay, so F is Earth-Moon distance. And that is going to be 3.84 times 10 to the 8th. And that is going to be greater than 3.1, so we're going to estimate 10 to the 9 here. Round up. So mean Earth to Sun distance, average, is going to be, Earth to Sun distance is 1.5 times 10 to the 11th. So we're going to estimate 10 to the 11th here, because this number is less than 3.1, this part right here. And again, Earth to Moon, Moon's pretty close to us, 10 to the 9th. Earth to the Sun's really far away, 10 to the 11th, that's only in a difference of 2 powers of 10. And these are just like really rough estimations, so keep that in mind. Now there's going to be a couple more. So equatorial radius of Earth. And that is going to be 6.38 times 10 to the 6th meters. And this is greater than 3.1, so we're going to estimate 10 to the power of 7. I is going to be the mass of an electron. And that is 9.11 times 10 to the negative 31. Now we're on the opposite side of the spectrum, so be careful about that. 9.11 is greater than 3.1, so we're going to actually move this a power up. We're going to be adding 1, right, for rounding up. So it's going to be 10 to the negative 30. J is going to be the mass of a proton. And that number is 1.67 times 10 to the negative 27. And this is less than 3.1, so we don't have to worry about it. So 10 to the negative 27 is going to be good for that, for a good estimation for that. And then the last one, K, is going to be the mass of the sun, which is sun 1.99 times 10 to the 30th kilograms. And sorry, units here. Draw kilograms, meters. Okay, so we're going to estimate that to be 10 to the 30th. That's the order of magnitude there. So now we're going to use all of these in order to answer some questions. I'm going to stop the video and then I will restart it and have the questions already written on the board. So give me 1 sec. Alright, I'm going to be stopping and starting this video pretty frequently so I can write the question down and we can solve it just to save a little bit of time. So this first question is how many electrons would it take to equal the mass of a proton? Well, we know the amount of electrons and we're using the order of magnitude to estimate this. So we said that the order of magnitude for an electron is, I think it was 10 to the negative 30. Is that right? Yeah, okay. So we have the mass of an electron equals 10 to the negative 30 kilograms. And then we have the mass of a proton, which is equal to 10 to the negative 27 kilograms, right? So we can just solve this using algebra. So if we have the mass of an electron, and we're trying to figure out how many of those it will take in order to equal the mass of a proton, which is 10 to the negative 27. Right? Oops, sorry, I'm going to actually do this symbolically first. Mass of proton. So now to solve for x, we can just divide both sides by the mass of an electron. Mass of proton over mass of electron. And that is going to give us x equals 10 to the negative 27 over 10 to the negative 30, which will give you x equals, you're basically subtracting the negative 27 will go away and you're left with 1 over 10 to the negative 3, which is the same thing as 10 to the third. So it's going to take 10 to the third, so it's going to take 10 to the third electrons to make the mass of a proton, which is a pretty big difference. So that is, yeah. So 10 to the third electrons will make that true. So I'm going to pause it and write the next question and keep going. So this question is how many Earths would it take to equal the mass of the Sun? Well, we have our order of magnitudes here. The mass of the Earth is going to be an estimate of 10 to the 25th kilograms. So mass, oh my god, can't write. Mass of the Earth is going to be 10 to the 25th kilograms. Mass of the Sun is going to be, I think, 10 to the 30 kilograms. And what we do now is we do pretty much the same thing, right? It's saying how many Earths would it take to equal the mass of the Sun. So 10 to the 25 is 1 mass of the Earth, right? I'm going to solve it symbolically right here. Mass of the Earth, how many of those would it take to equal 1 mass of the Sun? Which is M sub S. So 1025, which is the mass of the Earth, times X equals 10 to the 30th. So you divide these two, divide both sides by 10 to the 25th, and you get X equals 10 to the 5. It would take 10 to the power of 5 Earths in order to make the mass equivalent to the Sun. So this question is how many Earth-Moon distances would it take to cover the distance from the Earth to the Sun? So Earth-Moon distance is going to be, so from the Earth to the Moon is going to be about 10 to the 9 meters. And then Earth to the Sun is going to be 10 to the 11 meters. And remember, these are just estimates. So now we're asking how many Earth-Moon distances, so how many of these is it going to take to equal one of these? So 10 to the 9. We're going to do, just do it symbolically first again. So you're going to have an Earth-Moon distance multiplied by some number that will equal the Earth-Sun distance. So Earth-Moon distance is 10 to the power of 9 times x equals 10 to the power of 11. So 10 to the 9, you're going to divide 10 to the 9 on both sides. And then that's going to give you x equals 10 to the power of 2. So we'll need 10 to the power of 2 distances for that. So give me a second and I will write up the next problem. Alright, so a generation is about 1/3 of a lifetime. How many generations have passed since 0 AD? So, what year is it? Unfortunately, it is 2020. And, yeah, I'm sorry. Okay, so the generations are 1/3 of a lifetime. We're going to estimate this time that a life is about 60 years. Because 10 to the 9 seconds is a pretty horrible estimation, honestly. So, we'll do 60 over 3 is what a generation is going to equal, right? So how many generations were between the year 0 and 2020? So that means 60 over 3 is the same thing as 20. So we're going to have 20, how many generations, how many, right, is that x? How many generations until we get to the year 2020? Divide both sides by 20, and we get about, actually we get exactly 101. 101 generations have passed. So that's how you do that one. I was gonna do all of these for this little 1.1 on the scope and scale of physics, but it's pretty much the same throughout. I think I'm gonna try and start doing like a couple easy and a couple hard instead of just doing all of them. So I guess I'll be back next time. Thanks.